Okay, let's get back into stuff. So, any questions on the types of rules that we generated here? So, I'm never going to ask you something like this in a test because I don't know how they came up with this. So, this is something that I just think is completely brilliant, and it just came out of thin air, and I don't see any reason why they came up with it. But it makes intuitive sense in hindsight because we're just solving a bunch of subproblems. But to come up with this, I will never expect you to do something like this. Okay, so I'm definitely going to ask you one on midterm too. Okay, so any questions about the types of rules though?
Well, you're definitely going to ask?
It was a joke.
Oh, sorry, I'm just tired.
We're all tired.
Is there a general name for this?
I actually don't know. If you can find out, that would be great. I don't know if this appeared in a paper or something, or where this came from. I think CSE has references, but I haven't looked. I'm definitely sure it came from some paper because this is too important in the material for it to not be published somewhere. So I'm assuming it's from some paper. Like the DFAs were introduced in the 1950s in a paper, I would assume that these are too. Okay, yeah, so let's actually do an example. So let's do our simple PDA that we did for 0 to the n, 1 to the n. So I'm gonna recreate it here. And I'm gonna actually name the states because it will matter in this case. Let's see, so what did we do? So we did this, then triple epsilon, or if I can do it right, triple epsilon our way down to Q2, and then here we do the popping thing, and then go to Q3, which is a final state. Okay. So this is the PDA that we had before. So let's remind ourselves what the simplifications to the PDA we need to do. So what things do we need to do to the PDA to make it simpler?
One final state.
Yeah, one final state. In this case, to make it algorithmic, what should you do? Yeah, add a new one. Yeah, thanks. So you add a new one, and what did we do? We triple epsiloned our way over. I'm going to call it QF because I know it's the only final state. Okay, great. So what other simplifications have we made? I'm actually going to put this in a different color so we know what actually changed. Something I learned yesterday. Be able to change color of a whole set of things. It's so cool. Okay, so that was a change that we made. What are some other changes we made? Something to do with only the final state itself.
Oh, the loop.
Yeah, the self loops to pop off any excess symbols if we want to. Well, you can actually guarantee in this PDA that that will never happen because the only way to get to Q3 is to pop off that the only symbol on the stack anyway. But for sake of algorithmics, let's do it anyway. So what are the stack variables in this case? 0 and $. I could put additional symbols in the stack alphabet, but we never use them anyway, so we might as well just deal with it, with the two symbols that we have. So those two transitions were popping the $, doing nothing and not pushing anything, and then popping a 0 off and not pushing anything.
Hey, what's up with the 1?
Well, that is reading a 1, not the stack. So there's no push or pop with a symbol 1 on it. So we may as well just assume the stack alphabet has those two characters. I could put that transition in, but there's no point. Okay, what other simplifications did we make? Yeah, the transitions. Well, the Q0 to Q1, I think that's okay because it's doing one of the two operations. It's pushing but not popping. The 0 epsilon 0, that's also okay. It's pushing, no pop. Oh, the triple epsilon one, that's doing neither. So how did we fix that before? Yeah, we push something, doesn't matter what it is, and then pop the same thing. So what do you want to push? Let's do $. We got to pick something in the stack alphabet for it to work, for obvious reasons. So let's push on $, because we want to be rich, and then let's call this Q4, and then come back to Q2, popping that same thing. Okay. The self loop on Q2, is that okay? Yeah, it's fine. It pops something and doesn't push. That's okay. The 2 to 3 transition with the $, is that okay? Yeah, that's also okay. It pops, doesn't push. Fine. The self loops on QF, those are okay because they just pop some character and don't push anything. Oh, we have another triple epsilon transition. So let's actually do the same thing that we did before, which is to go to a new state. Let's push on $, again because we can. Call it Q5, and then go back. Got to rotate myself to angle it right. Then pop that same character off. So if I were to ask you this on a test to do this, this would be, as you can see, it could be a very big PDA starting from a small one because you got to make a lot of fixes to it and add a lot of states. And it's actually going to get a lot worse, as you'll see in a second. So are we done generating the modified PDA at this point? Yeah, that's all we needed to do. Single final state, every transition does one of the two operations exactly, and the final state just pops everything off. Okay, great. So let's actually generate the rules of the grammar pen. So what were the type 1 rules again? Let's familiarize ourselves. Type 1. Yeah, go ahead.
All right, real quick. For a test, if you gave us the original PDA, would you want to see us step by step go through, like add the new?
No, you can just do it all at once. Yeah, it'd be too much work for something so incremental anyway. So if I were to ask that, just do the whole thing at once. I mean, you can do it incrementally, then erase, then yeah. Okay, but if I were to ask you this, I wouldn't ask you anything that's more than like 4 states. So it'd be really small anyway. Yeah.
If they are pushing the dollars in the beginning, then why are you able to final state or will be going to the final state by reading the dollars?
So I think what you're saying is that when we go to the final state, we know for sure that the stack is empty. Yeah, so this is purely algorithmically. So to make this work for any PDA, that doesn't necessarily have to end empty. All the ones that we dealt with, they had to end empty in order to go to the final state anyway. But you can imagine a situation where every transition just pushes on a symbol. Actually, that's a great exam question. So what if we had a PDA that every transition either did nothing to the stack or just pushed, never popped at all? What is the language of that PDA? Well, if it never pops, does it ever inspect the stack? No. So does it need a stack? No. So what is the language of that PDA? Regular. Okay, so things like that, those are nice questions. But anyway, let's go back to this. So type 1 rules. So what are the type 1 rules here? Well, it says generate this rule for every state in the PDA. So let's actually do that. So how many states do we have here? 7. If I can count right. 7. So how many rules will we generate of type 1? 7. Yeah, because it's for each state in Q, make 1 rule. Cool. So I don't expect you to write 7 rules here. Let's just do 1. So let's just do Q0. So Q0, comma, Q0 generates empty. So that's an example of type 1. There are 6 others, obviously. Then you would have a Q1, Q1 makes empty, Q4, Q4 makes empty, and all the way through. So all we're doing is just looking at the state names and making a single rule for each one. Let's do type 2. So here's where it gets a lot worse. So let's see. We have 7 states, correct? How many type 2 rules are we going to make for all triplets of states? And they don't have to be different. Well, I have 7 choices for Q, 7 choices for Q prime, and 7 choices for Q double prime. How many is that in total? 7 to the third, which is 343. Do you think I'm going to expect you to write all 343 rules? No. Well, could your computer do it? That's the key. Yeah, it could, certainly. Let's see. And in fact, a lot of these variables are just going to be completely useless. Take, for example, A, Q1, Q0. All the strings that take me from Q1 to Q0. How many strings do that? None. So some of these variables are completely useless. But there's no harm in putting them in because it doesn't do anything. Because the variable won't generate anything. So we might as well just do this in general. So can any of you name 3 states? And they could all be the same, all different, anything you want. Name 3 states. Any 3. 0, 1, 2, perfect. So I would have said that for any triplet, but so Q0, let's just say that Q1 is the middle guy, Q0 is the start, and Q2 is our target. So the variable I want is Q0, Q2, because that's my start and my target. You can think of this like airlines. So if you are going to a destination and you have an overlay somewhere, so you're stopping at some airport and then going from that airport to the destination, that's exactly what we're doing here. So Q0 is our home airport, Phoenix. Q2 is our destination, and Q1 is our intermediary hop. So if we know how to go from Phoenix to this intermediary place, and then from there to our destination, we know how to get from here to our destination. So how do we get from here to our intermediary? Well, the state that was said was Q1. So if we know how to go from our home place to Q1, and if we know how to go from the intermediary place to our destination, then we know how to go from the start to the end. Okay? Does it at least make a little bit of sense? Any questions about type 2 rules? Let's do another one. Name a useless triplet of states.
72.
No. They have to be actually states. But name 3 states, I guess, and then we'll do them in backwards order to show that this has to work for any triplet. So QF, what are 2 others? Q5 and Q3. So let's do, our start is QF and our destination is Q3. And I'm not insane. Well, tonight I'm not insane. So, yeah. So go from QF to Q3. So then we got to go from QF to Q5. and from Q5 to Q3. So we'll just put even the useless ones in because they won't generate anything. And we don't have to make any decision about the PDA structure in order to do that. Does that make sense? Okay. Those are all the types of rules, right? Ooh, do we have another type of rules? Yeah. Okay, type 3, great. Let's just do only one example for time constraint reasons. So what do we need in order to do a type 3 rule? Well, we gotta yeah. Yeah, so it's for all triplets, whether or not they make sense. Yeah, any triplet at all, yeah. Yeah, so they don't have to be touching or anything. Yeah, so any triplet at all, yeah. So because there are 7 states, we're going to get 343 rules for that reason, because 7 cubed. Okay, we're just doing a few examples, of course. So what do we need for type 3? Oh, go ahead. Oh, no, there's not. Thank you. Yeah, that's not supposed to be there. Be more vigilant like her. Okay. Yeah, so that's not supposed to be there because it's concatenation. Okay. Type 3. What do we need for type 3? Yeah, so something about transitions. Well, we need one transition that pushes some symbol and another one that pops the same symbol. Okay? Doesn't matter which symbol as long as the same on both. So can you name a pair of transitions that has that property, that one pushes something and the other one pops the same thing?
Q1, Q2.
Yeah. Okay, so Q1, well, actually there's no transition from 1 to 2.
Oh, just kidding.
1 to 4 and 4 to 2. That's a perfectly good example. So let's do 1 to 4 and 4 to 2. So I'm just going to redraw these transitions. So Q1 to Q4. Oops, not F. Q4 is here, and then Q4 back down to Q2. So the first one is pushing on the $sign, and the other one is popping the $sign. So for type 3, what is our start and destination in this case? Q1 to Q2. So the left variable is Q1, comma Q2. So what do we need? We need to be able to figure out what do we read on the push transition? How do I get from the Q4 state to the Q4 state? And then what do we read on the final transition, the popping one? So what do we read on the push transition? Yeah, nothing. So there it is. How do I go from Q4 to Q4? What variable does that? AQ4, Q4. So AQ4, Q4. And what do I read on the final pop transition? Nothing. So, and that's it. So that's a rule that we generate. And look at it, just look at the PDA itself. If you want to know how to go from 1 to 2, you just figure out how to get from 4 to itself, which will turn out to be nothing. So in order to get from 1 to 2, you don't read anything, which seems correct in this case. Can you name a pair of transitions that actually do read something? Yeah, so the Q1 to itself and the Q2 to itself. So those are the only transitions I think that read. So let's do those. So this is the other example. Q1, Q2. The first one reads a 0 and pushes on a 0. The second one reads a 1 and, oops, got that wrong. Reads a 1, pops a 0, pushes nothing. So what is my start and destination here? Where do I start? Which is the beginning of the push transition. Q1. And where is my destination, which is the end of the pop transition? Q2. So to get from Q1 to Q2, what do? We read something on the push transition, which in this case is what? 0. So we generate a 0. And then what are my intermediary states here? So where does the push transition end? Q1. So I got to know how to get from Q1 to what? Q2. So I have the same variable in this case on the right side. And what do I generate on the end? On the pop transition? Yeah, 1. If you can speak a little louder, that'd be good. But yeah, think about what happens here. If you look back at the PDA, what it actually does, in order to get from 1 to 2, one way you can do that is generate a 0 at the beginning, a 1 at the end, and then recursively solve the problem with the same 2 states, which is exactly what the original PDA did anyway. It generated a 0 at the front, 1 at the end. Cool, so that's another rule that you'll generate. So in general, there could be a gazillion number of rules, a scientific number, that you will generate via here. So the key here is, can a computer actually do this? Or for type 3, did we need to actually do something special? Did we need to think cleverly about what to do? No, because all we did is iterated through all pairs of transitions, found a pair that matched, and then just blindly generated a rule like this. We didn't have to do anything special. So we can convert any PDA into CFG. I guess an equivalent one. Awesome. So in fact, PDAs are the right model for context-free languages. So now we have established equivalence, finally, between context-free grammars and PDAs. Pretty cool. Any questions about the example or anything that we've done with CFGs? Yeah.
What if there's a PDA that doesn't push and pop the same character for like the type 3?
It's a great question. So what if we, in the PDA that we're given, have every transition push and pop different symbols? The key is that the final state at the very end will have a pop for every single one of them. So there must be a push somewhere, because if there's a push, there obviously is a push. But if we have a flat transition, there's a push and a pop. And if we did a pop and a push, well, there's a push there. So there must be a match somewhere. Yeah, great question, Bill.
You mentioned that in the final state we pop all the symbols, but when we are taking the dollars, putting the dollar symbol, so aren't we enforcing that there would be equal number of push and pop?
Yes, there is an exact number, the same number of pushes and pops if we end empty, correct, yes. Because every push and pop will do exactly one thing to the stack. So if we start and end at the same place, we have the exact same number. That's correct.
So we can skip the dollar symbol if we have the final state and we are popping all the elements in the final state, right?
So which transition are you looking at?
Like from Q0 to Q1, we are pushing the dollar symbol.
Yeah.
If we are also doing the same thing, because necessarily.
Oh, okay.
The dollar symbol thing, or you do the final and
Yeah.
pop all the symbols.
I see what you mean. That would require an analysis of the PDA. So in this case, you can. But the thing is, I want this to be algorithmic and work for every PDA. I don't want to modify the structure of the PDA too much. So by leaving the PDA as alone as I possibly can, I don't modify its language. So I guarantee that it works. But you're right. In certain cases, if you wanted to actually make it easier or the PDA even simpler than this, you can do that, yes. But it's just we want this to be algorithmic.
Okay, I'm saying both the procedures are algorithmic, but they are both independent. If you just do the final state, like pop all the symbols at the final state, that's also algorithmic. Because you are popping all the symbols at the end, you are already accepted that state.
Yeah, so I'm not sure what the problem is
But
then.
if you don't do the final, like if you
Yeah.
don't do the popping in the final state, and
Yes.
do the dollar symbol thing, so we are enforcing that we have to pop all the symbols.
Yeah, so in this case, we guarantee that the stack will be empty by the time we get there anyway. So in this particular case, we can guarantee that, but in general, we can't.
As long as you follow the dollar symbol convention, then aren't we enforcing that?
Yeah, in this case we are, but in general we can't guarantee that. So I could, in this particular case, scratch this off. You're absolutely right, we can. There's nothing wrong with that. In this particular case, but I want this to work for every PDA, so we might as well just do the algorithmic process. But you're right, this would work in this case.
Can you give me an example like where you will need both the things, like pushing the dollar symbol as well as the final state, like popping all the symbols from the final state?
So what is the example that you're asking?
So you're predicating this with, or you're saying like this one can follow the dollar symbol, and you're saying, this has to work for every DFA or
Yep.
every PDA.
Mm-hmm.
So I think that miscommunication is there can be a PDA that exists that does not follow the dollar symbol convention, right?
Yes,
So
yes.
that's what would break your assumption and would render
Yeah,
that not
yes.
right.
So not every PDA does that transition at the beginning. It doesn't have to push a symbol immediately. Because a PDA could pop on its very first transition. It'd be a dumb PDA, but it could pop on its first transition.
So if we assume that as long as we're following the dollar sign convention, you're no longer dealing with general PDA.
Yeah. So I mean, you could do that dollar sign thing, but it's just I don't want to deal with changing the PDA if I possibly can. I want to leave the PDA alone.
If any PDA doesn't follow the dollar sign thing, so we can we do the epsilon transitions. Can't we do this thing as well to that PDA?
You'll have to show me an example after class because there's something I'm not understanding. Other questions?
We can move on.
Okay. So when we talked about regular languages, we talked about DFAs, NFAs, and regular grammars, regexes, and all that stuff. So when we established those four models are the same, what did we do after that? What did we show exist that are not regular? Languages that are not regular, right? So you may be thinking, okay, well, are there languages that are non-context free?
Yes.
Maybe. So let's look at this one. Well, we talked about 0 to the n, 1 to the n before, and we showed that that wasn't regular. Is that language context free, 0 to the n, 1 to the n? Yeah, because this is a PDA for it. Okay? Well, what about this example? What if we did 0 to the n, 1 to the n, 2 to the n? Well, this is obviously not regular. But is this context free? Well, think about how would you do that with a stack? If you saw an input that had zeros, ones, and twos on it, and you wanted to ensure that the number of zeros, ones, and twos was the same. Well, we could try our idea of put on the zeros as we read them and then pop off with the ones. But what do you do with the twos? Well, if we try to make another state, well, we still only have one stack to deal with. We got to put the zeros or something on the stack. Well, I can't just say, well, put the zeros on, then put the ones on, and then match the 2s up, because that won't work. Well, can you do this? Let's just think for, just as an example. What if we had 2 stacks instead of 1? Could you do this language with 2 stacks? Yeah, how would you do it? Push the zeros on the 1 stack, then push the 1s on the 2nd stack, and then as you're seeing 2s, pop off both stacks at the same time. Oh, so if this language is not context-free, which we haven't proven yet, but if it is not context-free, then 1 stack really is limiting. 2 stacks really is more powerful. So let's try to see what we would do with trying to show that something is not context-free. Maybe there are no non-context-free languages. Maybe everything's context-free. But let's just see if we can say something. Well, how did we proceed with regular languages? What did we do with a DFA? With really long strings, what did we do? Well, we looked at a DFA with some number of states, and then we fed in a string that had length equal to that number of states, at least. Then what we saw is a repetition of states, and then as long as we went around that loop as many times as we want, we could make a bunch of strings that went to the final state. So, and therefore are in the language. So let's try that same thing with PDAs. Feed in a long string, it goes around the loop many times, and then goes to a final state. What's wrong with that idea? What does a PDA have that a DFA doesn't? Stack. So if I go around a loop and come back to some state I saw before, could the stack change? Yeah, even if it was the same symbol, the stack height could have changed because I could have put more things on or taken things off. So it seems kind of hard to deal with PDAs then, because there's this temporal thing that will be specific to each of the computations for each string. Whereas with a DFA, it doesn't matter what the actual string is. When we came back to the same state, we might as well have just forgotten that entire loop, because the only thing you need to know about a DFA is what state you're in and what character you're about to read. That's all that matters. With a PDA, it matters because there's this temporal aspect with the stack. So PDAs kind of seem difficult. Well, maybe we can see something with CFGs. Are CFGs equivalent to PDAs? Yeah, so we just established that, so cool. So we might as well just proceed with CFGs because I don't see a way to do this with PDAs. Okay. Well, CFGs don't really have this temporal aspect because when you are generating something, the only thing that matters is the variable that exists right there. It doesn't matter what's on to the left or the right of that variable. So there's no temporal aspect here. Great. Well, even with that in mind, a normal CFG could be really complicated because we can put anything on the right-hand side of the rule. So is there a way that we can make CFGs simpler? Chomsky normal form. Does Chomsky normal form make the grammar easier? Or more simple, I guess, in the structure? Yeah. Oh, wait. Well, only some grammars can be converted to CNF, right? So we can't do this in general. Or can they? Can any grammar be converted into CNF? Yes. In fact, they can. So maybe let's try this. Maybe it won't work. It will. But let's just try. As I said before, there's no hurt in actually trying a new idea that may or may not work. In fact, in what I do, hundreds of ideas just don't work, and there's only one that does. But that's the key there. You're trying new ideas. So let's try this. So let's look at CFGs in CNF. And what did we do with DFAs when we wanted that long string to repeat a state? Well, for CFGs, we don't have states anymore, right? Or at all. So there's no state here to consider repeating. But do we have something that can repeat with a grammar? Well, with terminals, you're just generating those. Because once you generate a terminal, you're not going back to it. But there's something that can repeat otherwise, a variable. So we could have a variable at some point and then drill down into that and then have another copy of that same variable appearing. And then drill down deeper and then have another copy of that variable repeating. Oh, that's interesting. Let's try that. Well, let's see. Well, what could happen is, well, we have if we look at a parse tree for this grammar, well, the start variable is always at the top of the tree, of course. But what do we know about this tree, though, the parse tree itself? Well, we don't really know much, because it could be that right at the very top, there are a bunch of leaves on one side with the terminals and terminals on the other side, and then there are only variables in the middle. So it could be a very narrow tree. But let's just look at it in a general case. So let's actually refresh ourselves on what CNF actually is. So what rules are in CNF? What rule types are we allowed? So what are the three types? We can have the start variable making empty. We could have any variable making a single terminal, or we can have a variable making two variables. For a parse tree, what are the leaves of the parse tree? Always. Terminals, or epsilon, but terminals, really. What are the other nodes? Take all the leaves away. Just ignore those. What is left? Variables. So let's just imagine that we're going to make a tree without the leaves on it. So no terminals, only variables. What is the structure of the parse tree? So one level down right here, how many nodes are in that level? Can you guarantee? 2. Why can you guarantee 2? Because I have to create 2 variables. So we have 2 variables here. And then if you drill down deeper, well, maybe one of them dropped out early to make a terminal. But if we look at this in the general case, what do we know about this tree? Every single node in it has how many children? 2. Isn't that cool? By enforcing a grammar to be in CNF, all of the parse trees have the same structure. Maybe not the same tree, but the same structure. They're all binary trees. Pretty cool. So what is the thing that we want to repeat in the grammar? The variable. Well, let's see. Let's just say, for example, this is just purely an example. So let's just say that this variable made a single A and then this side made something else. So it's highly unlikely, if the grammar is big enough, that we're going to see a repetition on the right side here because it's pretty short. So assuming the tree is big enough, and we'll see what that means in a bit. If the tree is big enough, where should we be looking for a repetition of variables? Well, if the tree is tall enough, say at least the number of variables plus 1, where should we look for a repetition? We should look for it in the longest root to leaf path. If we look at the longest one, and assuming the tree is big enough, then there must be a repetition somewhere along that way. Great. So let's look at the longest root to leaf. It's not really leaf because we took off the leaves, but anyway, you get the idea at least. So let's restore our artist conception here. What type of tree is this again? Binary. So let's just say that there are H variables in the grammar. How high must the tree be? Oh, sorry, not that. How many nodes must there be in the tree to guarantee some repetition of variables somewhere? Yeah, so the height of the tree so the height must be at least h plus 1. You can actually do slightly better than that, but let's just say that's fine. So that must mean we need at least, let's just say, taking this into consideration. If it's a complete binary tree, which it might be, then if we have 2 to the h plus 1 nodes in this tree, then we have height at least h plus 1, which is enough for us. The number itself doesn't matter. The key is that it's a finite number, okay? So as long as we have a finite number, we're okay. Pretty much with everything in this class. Okay, so we're looking at a longest root to leaf path, which let's just say is this one right here. So going from the top and going down through, let's just say that this is the longest root to leaf path, and therefore there must be a repetition of variable somewhere in that grammar. It can't be the start variable, obviously, because it can't appear on the right-hand side, but let's just say that it's just some other variable a, which appears here, and then because there must be a repetition somewhere, the same variable appears somewhere else along that same path, because the path has more variables on it than there are actual variables. So there must be a repetition. Questions about that? Well, let's see. Let's try to understand something about this a variable right here. Knowing the rules of CNF, what do we know that a cannot possibly generate? The variable a, not s, the variable a. It can't generate the empty string. Fair enough? So let's see. Because it can't generate the empty string, it must generate something of the string, some non-empty portion of the string. Well, let's see. So the bottom a must generate something of the string. So I'm going to label that as a subtree rooted at this second a. And then the a before it must generate at least as much of the string. So the top a is going to generate more of the string because it's higher up on the tree. There's actually a more precise reason why that's true, but you can see because it's higher, it must generate more. Well, let's see. Let's label these 5 parts. So let's call this part, how did I call it before? U. Then this second part we're going to call V. This middle part right here we're going to call X. This part Y. And this part Z. Okay? Any questions about that? Okay, so like with the 3 parts that we did for regular languages, let's actually try to understand these 5 parts. So let's see what actually happens here. So let's see what happens. So let's look at this subtree right here, the one that has the A on top with the A appearing beneath it. So let's look at that further. So we have the A up here, and then we have this same path down to the bottom with an A appearing in the middle, and it generates something. Where is the closest possible place the second A, the one on the bottom, can appear after the first A? Where can it appear? What is the closest place it could appear? It could appear right after it, right? Well, let's see what happens then. So if we have that simple case where the second occurrence of A appears right after the first one, then we have something like this. And then this is some other variable that we don't care about. Well, let's see. We're only looking at one path from the top to the bottom. So let's see. What does this subtree generate? If we actually look at this. So this generates something of the string, and then this part generates the next part of the string. And they don't overlap because it's a tree. Well, let's see. Where is the X part? So what does X correspond to in this case? The thing that's generated by the second occurrence of A, not the first one. So the second occurrence of A is right here. Oh wait, what happened to the V here? It was swallowed up by the left side. Where's the Y part? It's on the other side. Ah, so the Y part is here. If I flipped the diagram and had the second occurrence of A on the left, what can you tell me about V and Y? Well, Y would be empty and V would be non-empty because the other variable must generate something of the string, okay? So what do you know about V and Y in general? Well, could they both be non-empty? Yeah, because the second occurrence of A could appear lower. Well, could they both be empty? No, because that would correspond to the A appearing on both sides and being swallowed up. But it can only, since we're only looking at one path, it can only be swallowed up on one side. So from this, we know that V and Y cannot both be empty. One of them could be, or both of them could be non-empty, but they can't both be empty simultaneously. Okay, great. That's actually the hardest part. Let's actually look at it a little easier. Well, let's see. What kind of grammars are we dealing with? Context-free. So this occurrence of A right here, either one of them, does it matter what was generated to the left or right of it, that variable A? No, it doesn't matter because it's context-free. So let's just try an experiment. Could I take the first occurrence of A and copy it down to where the second occurrence of A is? Just copy that whole subtree down. So what you would get is this. So you would get this path again. The first occurrence of A is here. And all I'm going to do is I'm going to recopy it down and generate this. And then I guess now the third occurrence of A is going to generate something. Just like before, I'm just copying a subtree down. Well, what is this string? What is the string that corresponds to this tree? Well, did the U, the beginning, and the Z part, did those two change? No. So those two didn't change. So they're still there. What are the things that changed? Well, we still have the V part right here and the Y part right here. And if you remember, the tree that was copied down had the VXY part. So the VXY part is here. What do we know about this string because it has a parse tree? Because it has a parse tree, does the grammar generate it? Yeah, because it's a parse tree. So what is this string? Well, it is a single U followed by two copies of V. There's only one X, two copies of Y, and a single Z. And we know that that is in the language because there's a parse tree for it. Could I do this 3 times, 4 times, 5 times, as many as I want? Yeah, I could just keep copying it down. Could I remove the X part in the middle? Sorry, not that. Don't listen to me. What if I did this instead? So instead of copying the first occurrence down to the second one, what if we copied the second one up to the first? So instead, you'll have something that looks like this. Looks like an A or something. So there's a U, there's a Z over here, if I can draw. And the X part is right here. So this is the path. There's an A right here, and it generates this part. Could I do that too? Yeah, because I'm just moving one subtree of A because it's the same variable up. What is the string here? If you just read the leaves left to right, UXC. So that corresponds to setting the exponent on V and Y to 0. Does that sound familiar? So that must mean that U, V to the I, X, Y to the I, Z is in L for all I at least 0. Nightmares reappearing?
Yes.
But so here's the thing to keep in mind. We're dealing with 5 parts instead of 3. And we have 2 parts to pump, but notice the exponent here. It's the same in both cases. So it's not there's a different number of V's and Y's here. It's the same number. Okay, great. So we got that. What was the other condition about regular languages? So we had the all I at least 0 condition and the non-empty condition. What was the third one with regular? Was there? Yeah, the length of the first 2 parts was at most P. And we saw that because if we looked at the very first time we looped, that couldn't have occurred more than the first P characters. So let's do an analogous thing here. So let's see, what is the part that is being repeated? It's this subtree that has the VXY part in it, because that corresponds to the variable A. So for that reason, how long could the VXY part be? Well, let's see. Think of a string that has exactly P characters that's in this language. Well, the occurrence of A here, could it be the very top? What is this top variable? The start variable. Could the start variable repeat? No. So it can't appear higher than the top. That's the key here. So if we deal with a string with exactly P characters, then what happens is that the VXY part couldn't have more than P characters because the entire tree is generating P characters. So if a subtree generates the VXY part, it can't be more than P characters. Okay? And the same thing is true if you're dealing with a string longer than P. Well, if you look at the bottommost occurrence of this variable A, where it repeats, then that can't have more than P characters for the same reason. So for those reasons, then the VXY part cannot have more than P characters. So, in fact, that is the pumping lemma for context-free languages. So, what is the difference here? And I'll let you go, I promise. So, what is the difference here? So, the difference is that we're dealing with grammars in CNF, even though we're not going to use those in the proofs. The key is that we made the tree big enough so that we guaranteed a variable repeat somewhere from the top to the bottom. Because each variable that's not the start must generate something of the string, we noted that we have to have these these sub-trees right here with the A's. And because of that, we can't have both sides of the tree being non-empty, the V and the Y part. Then we noted that we can copy the subtrees down because it's a context-free grammar. It doesn't matter where the variable is. It's the same variable. So that we can get a different string because it has a parse tree, it's also in the language. And then we noted that if you look at the bottommost occurrence of this repeated variable subtree, then it can't have more than P characters because we're looking at the bottommost one and we're looking at the repetition. Same idea as the DFA. So that's actually all we need. Next time tomorrow, we're going to prove some languages are not context-free. So I'll see you tomorrow.